Look at example number 4 about how many molecules are there in a container. So we have an ideal gas that occupies a volume of 100 centimeters cubed at a temperature of 20 degrees Celsius and a pressure of 100 pascals. So let's write that down as our given. Then we also hopefully recall that we have the gas constant, R, which is 8.314 joules per mole Kelvin. This might be something different from what you used in chemistry class because we're using more physics related units of joules, and we're using volume in meters cubed, we hope. And we don't want to be, you could use the other gas constant, which is in liters and atmospheres and moles, but this is the one that we're going to be really using often in this class. Okay, in part A, we're trying to find Na, the number of moles, so we'll just call that N, and in B, we're looking for the number of molecules, so we'll call that capital N. So, in our solution here for part A, hopefully you'll realize that to find the number of moles, we have the pressure, the volume, the temperature, the gas constant. We really are going to be using PV equals nRT, the ideal gas law. And we're solving for N, so it's the pressure times the volume divided by the gas constant times the temperature. Okay, once again, the common mistake that people are going to make is being consistent with choosing the right units. Now remember that this gas constant is in joules. This is really, if you think of it, it's really 8.314, and a joule is a Newton times a meter all over a mole times a Kelvin. So that pressure too is really 100 pascals, which is equivalent to a Newton per meter squared. So we're okay with pressure because you can see there's newtons here and there's newtons here, and we have meters squared here and a meters. But we got a little bit of a problem with volume and temperature. They're not in the right units. They've got to be in the right units. The temperature must be in Kelvin, as we learned in the last problem. So to convert this into Kelvin, we're going to need to add 273 to this. So really this temperature is 293 Kelvin. We also need to change our volume to meters cubed. And a lot of people struggle with this too because there's commonly we know, oh yeah, 1 meter is 100 centimeters. And then they start to think, well, what's 1 meter squared? And they think, oh, it's 100 centimeters squared. No, no, no. It's 100 centimeters multiplied by 100 centimeters. Or what's a meter cubed? A meter cubed would be 100 centimeters multiplied by 100 centimeters multiplied by 100 centimeters. So you really have to cube it. So converting this to meters cubed, we're going to write 1 meter cubed on top, and on the bottom we're going to write 100 centimeters, and that is entirely cubed. So that's going to give you a volume of 1 times 10 to the power of negative 4 meters cubed. Now you're ready to substitute in. So I would encourage you, when you do ideal gas law problems, you should substitute with the units included with the values. Otherwise you might tend to make a mistake and forget to convert your temperature to Kelvin, or converting your volume to the appropriate units of meters cubed, for example, in this problem. So the pressure here is 100 newtons per meter squared. We have the volume, which is 1 times 10 to the power of negative 4 meters cubed. Then we have the gas constant, which is 8.314, and we'll write this as Newton times meter all over mole times Kelvin. And then we have also the temperature of 293 Kelvin. And then before you start multiplying these numbers, check it out and make sure that their units all cancel out. Let's take a look. You can see the newtons here will cancel out with the newtons here. The meters squared and the meters cubed and the meter here, these meters cubed will cancel out with the meter squared here and the meter here. So all the units of meters cancel out. And finally, the Kelvin here and the Kelvin here cancel out. And you have 1 over moles. So really the final answer is going to be in moles. So your final answer for number of moles is 4.105 times 10 to the power of negative 6 moles. We just write MOL, that's the abbreviation for moles. Don't think of this as molecules, it just means moles. So that's part A. And part B is a kind of another chemistry question. How many molecules are there if you're given the number moles? And And you hopefully recall that Avogadro's number is 6.022 times 10 to the power of 23. Whatever stuff you want, molecules or atoms or per mole. So in this case, we're going to say molecules per mole. So we know how many moles we have, and we now know how many molecules there are per mole. So if we want to find the number of molecules, we're going to take the number of moles and multiply by Avogadro's number. You don't have to write this formula out. It's not a formula that's listed on your formula sheet, actually. You just really need to think of this in terms of units. So we're going to take the number of moles, which is 4.105, times 10 to the power negative 6 moles, and then we're going to be multiplying by 6.022 times 10 to the power 23 molecules per mole. And that gives you an answer of 2.47 times 10 to the power of 18 molecules. Once again, I should just show you that look at the units of moles, cancel it with the units of moles, so you end up with molecules, and that's consistent with what you're getting. Now, I should point out at this point that there is another way of solving for the number of molecules using a different form of the ideal gas law, which we haven't seen yet used. If you go back to your notes where we discussed the ideal gas law, you can see that all along we've been doing PV equals nRT. But then there's this other version right over here. This is sort of like the ideal gas law when you talk about all the tiny little molecules. So if you knew how many molecules there were in the gas, that would be a lot of molecules, then you could use this form. All right, but if you're dealing with the number of moles of the gas, N, then you'll use the first form, which is very typical. We'll use the first one. But let's just take a look at this one because N represents the number of molecules, and K with a little subscript B is something new called the Boltzmann constant, and it has a value of 1.38 times 10 to the power negative 23. Let's just see how we can solve that problem the same way with this version here. So let's go over here to our problem that we were solving, and we're going to just write it over here. PV equals NKB times T. That's the Boltzmann constant. So the number of molecules would be equal to the pressure times the volume divided by the Boltzmann constant times the temperature. So the pressure was 100 pascals. All right. The volume was 1 times 10 to the power of negative 4 meters cubed. And then we have Boltzmann constant, which is 1.38 times 10 to the power negative 23 in joules per mole Kelvin. And then we have the temperature, which is given as 293 Kelvin. Now, joule per mole Kelvin is, or joule is really a Newton meter. So let's change that joules to Newton meters. And if you multiply it all out, you'll get N is equal to 2.47 times 10 to the power of 18 molecules. So the same as what we got earlier, just a different way. And that's it for this example.